Welcome back to the course lectures on physics of nanomaterials. Let us start today with the first lecture of week 2 of this course. Till now, we have primarily given you a broad introduction and overview of the importance of nanomaterials and nanotechnology. In the third and fourth lecture, we gave you lot of applications and the need of nanotechnology for present day and also for future. We had also given you the ways the nanomaterials can be classified, and we had talked about the concept of confinement and confinement induced modulation, but those were mostly given with some broad examples without giving the associated mathematics and physics involved in the whole process. From this week onwards, we will start looking at each aspects of nanomaterials which are relevant to us at this level more in detail. So, let us start this first lecture, where I will talk to you about the quantum effects which drive the property modulation in nanomaterials. So, in today's lecture, we will quickly revise the basics and the types of confinement which are associated to a nanomaterial or nanomaterials. What is the basic quantum mechanical formulation that is used to explain the property modulation in nanomaterials, more specifically the particle in a box problem? And then we will end this lecture by introducing the concept of density of states and how this density of states can be modulated by changing the size of the particles. And in subsequent lectures in this week, you will find that as the density of states change, they have very significant impact on the properties of a given material. So, if you revise your previous week's lectures, we have seen that we have talked about nanomaterials. We have talked about nanomaterials which have one of the dimensions confined, two dimension confinement, and where all the three dimensions are in the range of 1 to 100 nanometers. So, let us start. So, basically you have an atom and arrangement of atom will give you a particle. That is what the whole concept is. So, you can have a 1D lattice where the atoms are arranged in one dimensions only. You can have then two dimensional lattices where the atoms are arranged in two dimensions and the interatomic distances are given by A. Generally, this is what we are talking about, that the interatomic distances are in the range of angstroms. So, this is what we actually talk about, and in schools we had seen that this kind of structures can also simulate the diffraction grating systems, and therefore, you see diffraction from crystals when an X-ray is incident on it. Then you have 3-dimensional structures where the atoms are arranged in 3 dimensions, and you can either talk about small crystals or you can also talk about bigger crystals. It just depends how many atoms you are arranging in a given crystal. And then you can arrange these atoms in various ways. You can have simple cubic, you can have a body centered cubic. So, you can have a body centered cubic means if you have a cubic structure, then atoms are arranged at the cube edges, and there is one more atom at the center of the unit cell. So, this is body centered cubic. You can have these structures. If you look into the corresponding cross sectional view of the body centered structure, you will find this is the way it looks like. So, if you take a cross section and look from the top, this is the way it looks like. And if you build the whole structure, so this is one unit cell, and then you start arranging the building block to get the final structure, that is the final particle. This is the way the structure will look like. So, you can have cubic structures, you can have tetragonal structures, you can have orthorhombic, rhombohedral, triclinic, monoclinic. So, you can have various types of crystal structure. Basically meaning, if you have a tetragonal structure means what? We have studied in other courses that A is equal to B, not equal to C, that is lattice parameter A is equal to lattice parameter B, but the C parameter is different, and the angle alpha, beta, gamma are all equal and they are equal to 90 degrees. So, basically you have the third dimension which is slightly different from the other two, and therefore, the arrangement looks different. Let us go a step behind. Why should a material actually form? We know that there are two types of forces which will act. So, if you have two atoms which are coming together, so you have atoms being arranged. So, first there would be attractive forces that would act, and beyond a certain distance the same atoms cannot come nearer to each other, and then they will repel, and there would be a competition between the attractive forces and the repulsive forces, and there will be an equilibrium where these forces would then actually stabilize and equilibrate, and the atoms will go on arranging themselves. This is what it means, that you have two competing forces. What are those? You have the attractive force which is there, and then there is a repulsive force. So, if you take the convoluted picture of these two dashed curves, this is the final curve which you actually draw as a function of force versus interatomic distances, and you will find that initially it is the repulsive force which can compete predominantly, but beyond a certain force there will be an equilibrium setting in, and then you will get the system stabilizing. And if you draw the same thing in terms of potential energy curve which we have been drawing, so you have potential energy as a function of interatomic distances. You have seen that you have two competing forces and initially you get the attractive force, repulsive forces, but then you get a convoluted picture and finally you get the solid curve which is given as the potential energy curve, and you have been calling it as asymmetric potential energy curve. What does this mean? That there is an atom which is at the lowest energy. So, this is the typical point where the energy will minimize and system would like to stabilize and the interatomic distances would actually be given in this manner. This is explained by the Lennard-Jones 612 potential, 612 potential because the exponents are of this order. So, this is given by the weakly attractive force and the first term is given by the repulsive force, and the parameters sigma and psi are corresponding to bond energy and length respectively, and they are obtained by fitting to a known property of a material. So, you know certain properties and then from there you can then estimate the value of these two parameters. So, now we know why atoms come together, then they arrange, when they arrange they give you a particle. Let us go a step back. When we started our basic studies in school, what was the simplest atomic structure which was taught to us? That there is an nucleus and around the nucleus you have the energy levels, and in this the electrons are orbiting. This is what we have been talking about. So, an atom has a nucleus which consists of protons and neutrons, and electron revolves around the nucleus. This is what we understand, and we have seen in the previous slide that each atom is associated with a given potential energy curve. So, each atom will have a potential energy curve. And if you look into the whole concept, this concept was actually proposed way back in 1900 by Drude, and it basically assumed that the valence electrons of a metal atoms become free to move throughout the solid. So, if you have a structure which is of metallic nature, then the valence electrons of these systems would, of these atoms would actually be free to move, and this was modeled using the concept of electron gas. And you had the corresponding model where the positive metal ions form a fixed lattice and the electrons move freely in a constant potential throughout the metal, because you have potential function associated with each and every atom, and various properties could be explained using these models. But there were certain shortcomings which could not be explained using these model which was proposed. Like, it suggested that there should be large electronic heat capacity similar to classical gases, but it was not observed experimentally. The model said that the resistivity should increase in metals in a manner which is linearly proportional to temperature, but it again failed. It failed to explain the features like photoelectric effect, black body radiation, and many more. The whole model was based on the assumption that electrons do not interact with each other or with the lattice ions before they collide, and then they can go in their own direction. The model assumed that the electrons do not interact with each other or even with the lattice ions beyond collisions. If you look into the terms like Lorentz number in Wiedemann-Franz law, when you calculate these parameters using the concepts given by the Drude's model, it was very different to what was being observed experimentally, and hence the model had its limitation, but at least it gave a direction in which lot of things could be explained. This model was improved by Sommerfeld in 1928 by introducing the concepts of quantum mechanics. It said that electrons obey the Fermi-Dirac statistics, energy states are filled according to the Pauli's exclusion principle, and only electrons near the Fermi level contribute to the conduction at ordinary temperatures. This could explain lot of features in the metal lattices and also could be extended to insulators and semiconducting properties. But it again had certain limitations, that it still assumed that electrons move in a constant potential, ignoring the atomic lattice periodicity. It could not explain the origin of band gaps. Why we should talk about band gaps and why is it important? Because based on band gaps, you have three types of systems. What are those? Metals, insulators and semiconductors, and they are all defined in terms of the band gaps. And if a model is unable to explain this very important concept, clearly it had its own limitation, which could then be solved slightly bit later by modifying the first two models and introducing the concept of nearly free electron model. The Sommerfeld model also ignored the effects of electron scattering from the lattice vibrations, that is the phonon vibrations. So, there were models which were explaining the features that were observed experimentally, but then came the field of nanomaterials, and people started making materials with very small sizes. They started going and fabricating materials in the range of 20, 50, 100 nanometers or plus minus, and which model to actually use to explain the features which were very different from what these two models were actually predicting. How do you actually explain these two features? And that brought us to the requirement to define new terms, introduce new concepts which are now easily predicting the property modulation observed in nanomaterials. The first thing which was explained was using the concept of confinement, which meant that electrons in nano size materials can no longer be considered fully free. They are actually boxed in. That means they are forced to move inside a confined area, and the moment this thing was realized, it meant that the quantum mechanical formulation which is used in a particle in a box model could be used to explain the quantum confinement effect, which modifies the energy levels, and once the energy levels are modified, how the property actually changes. So, once again, what is electron confinement? Electron confinement, which is also known as quantum confinement, is a phenomena where the movement of electrons within a material is restricted to a region of space that is smaller than their de Broglie wavelength. This is the term which is used, and this is the definition of the term electron confinement or quantum confinement. And immediately the concept of wave particle duality came into picture. Why does this matter in nanomaterials? Because you can have various types of nanomaterials, meaning that you can have nanomaterials which have one of the dimensions in the range of 1 to 100 nanometers. You can have nanomaterials which have two dimensions in the range of 1 to 100 nanometers, and you have another set where you can have all the three dimensions in the range of 1 to 100 nanometers. So, if you have different types of materials, you will have to have different concepts brought together to explain the features which are observed. If you have a system where only one dimension is having confinement, so you will use one dimensional particle in a box problem, and when you talk about properties in one dimension, whereas the other two sides can be explained using the classical models, and then you can talk about this further for 2-dimension and 3-dimension confinements. So, therefore, the concept of confinement became very important in the field of nanomaterials. So, you have a simple animation which is showing the confinement which we are talking about. So, you can have 1D type confinement, forced to move in one dimension, 2D type confinement, you are forced to move in a planar structure, or 3D confinement where you can move in all the 3 dimensions. So, let us understand what is this concept of particle in a box. We have been introduced this concept of quantum mechanics at various places. Let us see a live example of that field. Sometimes we do a lot of mathematics associated with this problem, but what is the real application is lost in this whole process, but it is a beautiful problem and with large number of real life applications. So, when we say let us consider a box of dimension 0 to a, then what do we mean? That means we have, for example, a particle which has a dimension of a. So, you have particle from 1. So, you have a particle of size a. So, you have atom, you have electrons. So, within this particle, and it is a stable particle, then it means that whatever the electrons or free electrons we are talking about, they are going to move within this particle. This is what we are talking about. So, you have a box means in our case a particle of dimension a. So, let us say in the range where potential is 0, then we are in this region. Why? Because the particle is within this region and free to move. But electron or a system other than this, but electron, for example, cannot jump outside this particle. At this level, please do not go beyond what we are talking about, because some of you understand the concept of quantum tunneling and so on and so forth, but at this level we are just building our whole formulation. So, for the time being, we will believe that given this condition, that if you are at the boundaries, the electrons cannot jump out and will remain confined in this region. So, at the boundaries the potential is infinite, means that any entity, let us say electron, cannot jump out. So, this is what we have. So, in the range x more than 0 less than a, you have v is equal to 0, and if x is more than 0 or is more, and if x is less than 0, that means you are in this direction or you are in this direction, the potential is infinite. So, energy states of the particle of mass m can be obtained using the time dependent Schrodinger equation for one dimension. The whole formulation says that kinetic energy plus potential energy is equal to the total energy. So, you can write these terms, the time independent Schrodinger equation, and you will get minus h cut square by 2m delta 2 by delta x square phi x plus V x psi x is equal to E psi x, where psi x is the wave function. So, this is what the Schrodinger equation actually tells you. Let psi x have a general form given by this equation. What have we understood till now? That the particle exists only inside a box. Which particle we are talking about? Here we are talking about there is an atom, and electron is confined to move within the boundaries defined by this particle. So, you have electron which is moving in a box which is given by our nanomaterial. Wave function should not exist outside the box, because what is wave function doing? Wave function is giving you the probability of finding a particle. If you take the modulus, then it will give you the probability, but there is no probability of finding any particle outside the box. So, you cannot have electron outside the given particle, and it should also be 0 at the boundaries. So, at x is equal to 0, you have the condition, if this is psi x is equal to 0, that means b is equal to 0, and you have the term psi x is equal to a sin 2m e by h cut square, where h cut is equal to h by 2 pi, where h is the Planck's constant, under root x. At the boundary x is equal to a, you again have this condition that psi x is equal to 0. This leads to the condition psi a is equal to 0, means a sin 2 m e by h cut square under root into a is equal to 0, but amplitude a is not 0. Therefore, what you get? You have the term psi 2 m e by h cut square under root into a is equal to 0. This gives us the relation 2 m e by h cut square under root a is equal to n pi, where n can be 0, 1, 2, 3. Can n be equal to 0? Can it be there? Yes or no? Before you go to the next slide, think and answer, and then only go to the next slide. You will see that n is equal to 0 means psi n is equal to 0 and are not allowed inside the box, because if allowed, that means mod of psi n square would be 0 and psi cannot be 0 inside the box. That means outside also there is no probability, inside also there is no probability of finding the particle. Then where is the particle? So, physically it becomes incorrect. Mathematically it may be true, but physically it becomes incorrect, and therefore you cannot have n is equal to 0, and hence n takes the value 1, 2, 3, 4 and increases. Therefore, you get the term E is equal to n square h cut square pi square by 2 m a square, that is equal to n square h square 8 m a square. What does it mean? Energy is proportional to n square. Putting this E n value in the equation given in the earlier slide, you have psi n is equal to a sin n pi by a x. Now, you will ask a question, why is it important? Fine, I have solved the probability, but look at this value of a and look at the value a here. Now, let us put a equal to 10 nanometers and calculate E1, E2, E3 and so on. Then you have a is equal to 50 nanometers and we calculate E2, E3 and so on. Have a equal to 1 nanometer and calculate E1, E2, E3. Clearly, these values would be very different, and you can have any other values. So, just by changing the dimension of the particle, you have the E n values which are different. And similarly, the probabilities of finding the particle, that is an electron in a given box, that is the particle, would also change significantly by changing the value of a. So, it is very clear that the dimension will have significant on this E n values. But what is that? Let us plot it. So, if you see the E n value as a function of dimension, so n1, n2, n3 and so on so forth, you can clearly see that there is discreteness. So, you have discrete energy levels from one level to other. So, if you want to have energies where electrons are supposed to jump from here to here, you will have to give a significant amount of energy, so that the electrons can jump from the level n is equal to 2 to level n is equal to 3. Now, you make a quite large, let us say 1 micron, then what will happen? The energy levels will come very near to each other. And they would look like as if they are continuous. They are not continuous, still there is discrete net, but they are so close to each other that the electrons can jump from one state to the other, to the other, to the other, and so on and so forth. And then you are talking about the classical picture. So, immediately you can see that when you go to very small sizes, the quantum mechanical picture comes into the forefront, and you have the concept of discrete energy level and quantized energy levels coming into picture. And you have, now you just go on changing the size, you can get different energy differences between the energy levels, and you can tune the system, you can tune the properties. If you plot psi n for a given system. So, psi 1, this is the probability of finding an electron, psi 2, this gives the probability variation of finding, and then so on and so forth. If you plot the modulus, then you have this kind of curve. So, just by changing the size of the particle, you can change the wave function value, or you can have the change in the modulus, and you can then estimate where are the probabilities highest to find out a given particle. And that gives you a very clear explanation why there is property modulation when you have size reduction, because once the energy levels change, your electrical properties, your optical properties, your electrochemical properties, and associated properties would change, and hence just by changing the distance between the energy levels, you can change the properties in nanomaterials. Then there is another term which I will introduce today, and we will discuss more about them in subsequent lectures, is density of states. It refers to the number of available quantum states per unit energy range at each level that the electrons or any other particle can occupy in a material. So, this is basically d, which is a function of E given by dN by dE. So, if you consider, let us say 1D problem which we discussed, then E n is equal to n square is equal to h square by 8 m a square, and you will find out that d E is equal to dN by dE is proportional to e raised to the power of minus half. So, what happens that as you increase the energy, the density of states go on decreasing. So, you have less number of electrons which are there at higher energy levels, and the consequences would be discussed after we have also understood the whole formulation using the free electron model or nearly free electron model. Sometimes we believe that quantum mechanics and classical mechanical treatments of a material are two independent routes. No, they actually converge to the same information, provided we look at the whole picture comprehensively. They actually give us similar information, we should just look at the comprehensive picture. So, in today's lecture we have talked about the way materials form, and when they form they have certain dimensions, and when you go down to nanoscale you have to talk in terms of quantum mechanical pictures, and they have clear explanation why property modulations will occur when you reduce the size, and even within the range of 1 to 100 nanometers when you make materials of different sizes, you will have different nanomaterial of the same molecular formula. For example, you can have AbO3 type structure of barium titanate, let us say barium titanate nanoparticle. So, barium titanate nanoparticle of 10 nanometer would have slightly different properties from barium titanate at 20 nanometers, 30 nanometers, 35 nanometers, 100 nanometers. So, you can make the same material which is having the same chemical formula, but it will give you different properties, just modulate the size of the particles. Now, you can imagine the gamut of application this small concept opens, that slight change in the size will give you a new application of a given material. So, you do not have to do anything complicated, and therefore, nanomaterials and nanotechnology is becoming so useful for us, because although it seems to be difficult and complicated, it is a very simple concept. If you understand it and if you have the capacity to make that points clear, then you can get lot of applications. These are the resources from where certain points were taken, and you can refer to these books for more information, and thank you very much.